So I'm pleased to introduce today's speaker, Professor Jacques Delabrouille from Lawrence Berkeley National Laboratory. So he is widely recognized for his expertise in cosmology with a focus on cosmomicrowave background radiation. So he has been key figure in several high-profile scientific missions, most notably the Planck satellite. So he earned his doctorate from University of Chicago and University of Paris Sud Orsay. So currently he is affiliated to CNRS UCB International Research Laboratory and Lawrence Berkeley National Laboratory, where he actively contributes to various forthcoming CMB mission. So today he will talk, the title of his talk is Planck Revisited. So where he will talk about improved foreground maps and CO maps that is recently excited from the Planck data. So over to you, Jack. So the talk is roughly 40-45 minutes and then followed by questions. Yeah, you can share your screen here. Let's start.
Okay, it's a pleasure to be here and to talk about a project that I'm working on with some collaborators, which is to look again at Planck data and try to improve Planck data products. So I call that effort Planck Revisited. And let's see, how can I? Okay, sorry. So since this is CMB Bharat, I don't think I have to make a long introduction about the Planck space mission, but just to give a few facts. So Planck was launched by ESA in 2009. It's still at this time the most sensitive full sky survey in the 30 to 857 gigahertz frequency range. It has 9 frequency channels, 7 of which are designed with polarization capability from 30 to 350 gigahertz. And Planck data products are the reference, I think it's fair to say, for sky emission in this frequency range for the CMB and for galactic and extragalactic emission. And I should stress that this is for full sky maps, okay? Still, there are limitations to the Planck data products. They have been produced with stringent time constraints because we had to, write all the papers, get all the science, and within some constraints which was imposed by ESA. Then the knowledge of the instrument and the limitations of some of the products was obtained gradually within the Planck team during the data analysis. It was incomplete at the time of production of some of the results, even the final results, and there was no time to iterate much. Also, some of the products have been obtained with data which was before all the data was connected. So some of the intermediate or early products were obtained only with partial mission data. So now, after the release of the official 2018 data products, there is an opportunity to go back and try to yet improve some of these data products. And this is the objective of the Planck Revisited effort. I want to stress, to be fair to my colleagues, that there is a somewhat similar objective which is pursued independently within Cosmoglobe. And I will compare, in fact, some of the things we are doing with what has been done with Cosmoglobe. And today I will specifically talk about data products for polarized synchrotron and for Milky Way CO line emission. So it's foreground science and foreground data products. I have collaborators who work also on this Planck Revisited effort, in particular Mathieu Remazey and Shamik Ghosh, who participated to the production of the CO maps I will be showing later on. There is also Elisa Russier, who is currently working on dust maps, but I won't talk about what she is doing today. Okay, so let me start with the synchrotron. So the paper has been submitted in March and has been accepted in April of this year. It's currently under press. And so it's a low-noise synchrotron polarization maps from WMAP and Planck. The polarized foregrounds are very important for the present and the future of the CMB, because foregrounds are a key issue for CMB polarization measurements, in particular to look for CMB primordial B modes. And to that effect, we need to monitor contamination by polarized synchrotron and polarized thermal dust. Polarized synchrotron comes from energetic electrons in magnetic fields in the galactic interstellar medium. And typically, the emission as a function of frequency and sky pixel is some scaling of a map at some reference frequency nu zero as a function still of sky pixel, multiplied by a frequency scaling, which is approximately a power law of the frequency. And the spectral index is around -3.1 in Rayleigh Jeans units, with some variations across the sky, but these variations are small. Observations with Planck and WMAP are noise-dominated in clean regions of the sky, and the clean regions of the sky are the regions where we want to have the best possible map, because this is where we want to look for primordial B modes. And so the main enemy, I want to argue at this stage, is noise. Sky models, which have been developed using Planck data, and for Planck, the PSM, the PSM, are uncertain. They are models with some randomness sometimes. They vary from model to model in amplitude complexity, and they cannot be trusted to predict the contamination. So one should not just generate a map using one of these codes and try to use that as additional information to analyze real data. They are useful as training playgrounds to develop methods to separate the components, but one should use caution when combining them to real data. And getting additional full sky foreground observations from the ground is challenging. So for synchrotron, we have two official Planck products, one obtained with a commander framework, which is fitting a parametric model to multi-frequency observations, and the SMICA maps. So SMICA is spectral matching ICA. It's a blind method which uses correlations between maps at different frequencies to extract the spectra and the statistics in general, and the mixing matrix of the various components, and then use that to separate the observations into several components. The main obvious path for improvement for these two data products is that these data products have been obtained solely from Planck data, and they can be improved by including WMAP observations. And then one can also improve the characterization. If you look at these data products, the noise properties are not very well described. We have jackknife maps, but still, the beam is not completely clear. There is, in principle, they are produced at 60 arc-minutes, but there is additional smoothing, some kind of Wiener filtering probably, or some regularizing kernel, which makes it that the actual angular resolution is slightly different. And the error budget is not very clear either. So we can try and improve that. How good are these various maps? So here I've taken the lowest frequency channels of WMAP and LFI and just computed the power spectra of some jackknife maps corrected by the beam. Beams which range from about 52.8 arc-minute from K. It's not exactly a Gaussian beam. We see here some of the effect of some of the bounces of the actual beam, and ranging down to 27.9 arc-minute for the LFI 44 gigahertz channel. So looking at that here in linear scale in L, we have the impression that the sensitivity is dominated by the LFI 30 gigahertz channel, which is below, the noise is below, and this is log space, right? This is log scale. All of the other ones, almost everywhere. However, in these regions, which is of particular interest for detecting primordial B modes, we see that in fact the WMAP K becomes slightly better than than LFI. And by the way, this is all extrapolated to 30 gigahertz with this spectral index, beta S equals minus 3.1. So we can compare them because they observe the synchrotron at different frequencies. And so direct observation requires rescaling to compare the signal to noise ratio. So here what we see now is something which is proportional to the inverse of the signal to noise ratio squared. There is another thing, which is that the regions of deep observations are not the same for WMAP and for Planck. So this is now maps, again, scaled to 30 gigahertz of the noise level for WMAP K and LFI 30. We see that, in fact, the noise level is lower in the WMAP K, in particular in these regions, but there are regions of deep integration with Planck here, close to the ecliptic plane. Ecliptic poles, sorry. And there we have these rings of good signal, of low noise for WMAP, which are in regions where maybe the Planck data is not quite as good. And so we want to make use of that to generate a map which takes the best of each observation where they are deeper. I can show you maps, in fact, of noise for all of these 5 channels. So this is here LFI 30 gigahertz, now WMAP. Now we change color scale, multiplied by 3. This is Ka. Ka is very similar to K, but it's more noisy because the color scale has changed. This is Q. Q is interesting because you see that this ring here is not at the same location as for the other 2. And also the sensitivity has changed here close to the ecliptic poles. And now this is the LFI 44 gigahertz, which has this strange pattern of deep patches. And also, again, we see the shape of the Planck scanning here in these stripes here. So what the plan to get a better synchrotron template is to use these 5 maps. I don't think it's useful to use maps at other frequencies because the signal to noise becomes very low, and then we have to worry about dust contamination, and we have to worry more about CMB. And so using just these 5 maps is almost optimal. And we work in needlet space because we want to take into account the fact that the sensitivity of the maps varies as a function of scale, so as a function of L, but also in space, as I have just shown you. And so the idea is just to take these maps and combine them with weights that minimize the noise. So here's the pipeline. Polarization is the focus. We first put all maps at the same angular resolution, which we can pick something between 40 and 60 arc minutes. Same pixelization. Here I write n side equals 512, but for the final products, I did it at 1024. We subtract the CMB. The CMB is a very small contamination at these frequencies, but it's not completely negligible. So what I do is I make a Wiener filter version of the SMICA CMB, and I do a multivariate filter. So I use also the correlation between E and B to get a slightly better CMB map. And it's Wiener filtered because in subtracting the CMB, we don't want to add more noise than we subtract CMB. We put all the maps in synchrotron units, which means it's essentially rescaling them to 30 gigahertz to our reference frequency. And the reference frequency is picked at 30 gigahertz because it's sort of in the middle of the frequency range where we have the channels we are using. Then I do a special needlet transform. Special because usually what we do for needlets for polarization, we go to from IQU to I, E, and B, and then we work with B and E maps. But here I don't want to do that. I want to work with Q and U because as I will show you later, the sensitivity is different for Q and U because of the direction of scanning. in WMAP and in Planck data, and also E and B, the transformation into E and B is not local, and we want to use the local properties of the maps. We compute the noise level of each channel in needlet space, and then we coadd simply the maps with inverse noise variance, and we recombine all of that into synchrotron Q and U maps and E and B maps. And then we generate error maps, both for the noise, so this is additive errors, and for errors which we make in assuming some frequency scaling for the synchrotron. These are the multiplicative errors. So before I move forward, let's just have a look at the power spectra, rescaled again with this beta S equals minus 3.1 for these 5 maps. So this is a near full sky. There is just a point source mask, which is shown here, where we cut a number of point sources in the galactic plane and some of the well-known radio sources. And so what we see here is that the E modes are significantly higher than the B modes. The ratio is about 1/3 here. We see some bumps here around the L equals 6C to 70. These are masking artifacts. It's because there is some regularity in these cuts here. And so it generates structure at this particular scale, which is due to the mask. It's not something which is in the synchrotron maps. What we read also on these spectra is that the signal-to-noise ratio gets to about 1 over this almost full sky region at L equals about 200, so on the degree scale. And this is what justifies the fact that we will produce maps at degree scale. If we look with some more masking, so here masking the brightest region, in this new region, the signal-to-noise ratio for the best channels is about 1 at L equals 100, which is 2 degree scale. We also note, interestingly, that the ratio, the discrepancy between E and B, the level of E and B modes has decreased. This is easy to understand because most of these higher E modes is due to the geometry of the galaxy. And so when we mask much of the galaxy, it's reduced. And if we look at the region with the lowest synchrotron emission, again, the signal-to-noise ratio is 1 at even lower L. We have some scatter between these various measurements, and we see again here that the sensitivity of the LFI and K channels here are comparable. Oh, I take advantage of this to make a small advertisement for my masks. I put a lot of effort into doing these masks, looking at things very carefully. And so I think these are good masks for the synchrotron if you want to cut the sky in 3 regions of varying level of emission. So I encourage you to use them. They are available. I will show you where. And so, they are in particular, they are well suited to do analysis on intermediate scales, and they capture the regions of emission as a function of what we're interested in. There is also a point source mask, which masks some of the very well-known sources. So here are some quasars, Virgo A, Radio Galaxy, Centaurus A with big lobes here. Fornax A, LMC, etc. And then there are some various point sources, the Crab Nebula, of course. I put here M31, although it's not a big radio emitter. It was just because it's our closest neighbor. Okay, so this is I've shown what is the pipeline. So I skip some of the steps and just make a comment about putting all of these maps in synchrotron units, so scaling them. What is the impact of picking minus 3.1, while we know that there is in fact a little bit of variation of the spectral index across the sky? So we can see here the mixing column for the synchrotron here in red for minus 3.1, and what we have for other values of beta S. And we see that the difference is at most a few percent. So it means that typically we will make errors of the order of a few percent of the emission. So when we are in regions with high noise contamination, the signal is subdominant, and the error we make by picking this value is a few percent of the subdominant signal, and so it's small. It's a choice, right? We choose not to fit for beta S. What we gain is better sensitivity, lower noise, but with a small multiplicative error, which we will quantify later. So now, for the needlet transform, I picked 20 bands, which are shown here in log, sorry, here in log and here in linear. They are completely regular. And the reason I picked these bands for this project specifically is I want them to be wide enough to be able to localize at degree scale. That means that they must be about 100 or 100-ish L, which is what I did here. And they are narrow enough that they can sort of adjust to the varying noise level as a function of L because of the various beams. And they are, as usual, normalized so that the sum of the squares of the band equals 1 over a wide range of L, except here for the last band. I don't complement it with a half band here. So here we have a little bit of apodization of the beam at between 950 and 1000. So with this Y special needlet transform, we start from SkyMap, we go to ALM ENB as usual, filter them using the bands, and then transform back to Q and U and not ENB for the reasons I explained. And then we get these needlet maps, which we can combine with optimal weights as a function of where we are on the sky. And then we will do the process back and get back to coad everything, okay? So an interesting thing is what are the weights? So this is for the first band for larger scale, less than 50. As you can see, so we have here, so these are maps and the weights sum up to 1, okay? So we don't have much weights to channels K, Q, and LFI 44. Everything is done by these two channels, WMAP channel K, Planck 30 gigahertz. And you can see that the weights vary quite significantly across the sky. They range from Planck does it all in these regions here to WMAP dominates over a large fraction of the sky, in fact, here. And, with this kind of variation. These are an interesting thing is that the weights, as I mentioned before, are different for Q and U. These are the weights for Q. They are the weights for U. As you can see, these patterns here don't have the same shape. It's because of the direction of scan of the various detectors. This is now for a band we are much interested in. So this is between 50 and 150, where we could hope to detect the recombination bump of primordial B modes. These are the weights. Again, we are still dominated by the K and 30 gigahertz, but now the 30 gigahertz is more important because you can see it's slightly more towards yellowish and red here than here. And again, Q and U. And now, if we go at a high L channel, we can see here that most of the job is done by the F30 gigahertz channel, but not all of it. There are regions where about half of the weight comes from these other channels because it turns out that they are less noisy in these particular regions. And of course, these weights, they appear like that in the needlet domain, but then when we go back to real space, these weights will be sort of spread out. They will be smoothed by the inverse needle transform again. Then we recombine this into synchrotron Q and U maps and E and B maps, which I can compare. These are the SMICA and Commander maps, which you can download from the Planck Legacy Archive. This is what we get with this process at 60 arc minute. It looks similar, first order. And this is the Q map, and this is the U map. So here it's not very easy to see the improvement, but we can compute the polarized intensity. And this is the polarized intensity for SMICA. And this is the polarized intensity for this U map. So I don't know how well you can see on your screen, but on my screen here, it's very clear that the angular resolution is better and the map is significantly less noisy here than here. And now comparing with the Commander map, this is the map we get with this analysis, and this is the Commander map. They are not too different, but again, we see by eye that the map has better angular resolution, more well-defined patterns and structures, and is significantly less noisy. We can do noise comparisons. In fact, this is the noise for the WMAP K channel generated with 50 simulations and putting them at 60 arc minutes. The mean is 5.32 micro-K CMB. This is the same type of map obtained from the Planck LFI 30 gigahertz. We see that it's better. It's essentially because of the beam, because this is integrated over the whole spectrum, harmonic spectrum to 60 arc minute angular resolution. The mean is 3.776, and this is the combined map. So the mean is still lower, 2.79. You can see it's very significantly better than this and that. Okay. If we look in the power spectra, so we compute the power spectrum of the map, this is what we achieve here. And these are the power spectra which can be computed from individual channels. You can see that here we have an improvement of more than a factor of 2. So it's not just averaging. We also use the fact that there is a pixel dependence. And, as expected, the noise we obtain is lower than any of the other noise at all L. We can see how well we compare. We can compare the sensitivity we reach here in this particular region from 60 to 100 in L. We get on average an NL of this value here. And this corresponds, if we extrapolate with, again, minus 3.1 to about 145 micro-K arc minute at 30 gigahertz, 5 micro-K arc minute at 95, 1.7 micro-K arc minute at 150, which we can compare to the sensitivity of the ongoing surveys and the future surveys. It's not quite as good enough for completely correcting CMBS4, but these kind of sensitivities are, for instance, comparable to the sensitivities in these channels that we can get with Lightbird, for instance, or with Simon's Observatory. So for the characterization of uncertainties, so there is the noise maps, but we can also generate maps of what are the multiplicative error by repeating the process, but drawing at random beta S with a mean of minus 3.1 and sigma of 0.1. And so we do Monte Carlo simulations and then compute the standard deviation of the set of maps we get. And this is what we have. Not surprisingly, it's proportional to the signal we are measuring. This is here for polarized intensity again. And this here is the sum of the noise contribution and of the multiplicative error. So we see that the multiplicative error is not visible anywhere except in the center of the focal plane. in these maps. Okay, how am I doing with time? Okay, not too bad. Recently, there has been a paper by Watts et al. Who describe products obtained with Cosmoglobe. And they make this comparison, which is very similar to what I've shown you between K and 30 gigahertz and the Cosmoglobe product. And it's not very clear to see the difference on these maps, but here again, there are noise maps, which include also some multiplicative uncertainty, which is probably due to errors here, in calibration errors, which impact the data, in particular in the galactic plane. And we see that also with the Cosmoglobe product, they have this nice feature that we see lower noise in regions where one or the other instrument is doing better. And here there are maps of which are shown here in this small square here, which supposedly show that the noise level is lower in Cosmoglobe. So I went out and decided to compare what I got with these maps. And so here are the spectra computed in this central region, not the galactic ridge, but the first mask, which corresponds to the highest signal. And so the power spectra I compute for my maps are in black and gray here for E mode and B modes, and the Cosmoglobe are in red and orange. And what we see is that they are in very good agreement here at low L, and then they start to depart. There is a little bit less power in the Cosmoglobe maps than in my maps. And it becomes even bigger here. When we go, this difference becomes even bigger when we go to higher. And the question is, what is that? Because it could be two things. In principle, the maps are the same angular resolution. So if one is lower than the other, it would mean that there is less noise. But in fact, no, because in the Cosmoglobe process, there is a smoothing kernel, which is used to regularize the fit. And I discussed this with Duncan Watts, and he mentioned that it's plausible that this generates additional smoothing. So what I did is I computed the ratio of the spectra here after correcting for the noise bias for the Planck revisited maps and using a cross spectrum for the Cosmoglobe. And here is the power ratio, Cosmoglobe over Planck revisited, for B modes and for E modes in gray and black. And I overplot here a 30 arc-minute Gaussian beam. And you can see that, in fact, this ratio is compatible with extra smoothing in the Cosmoglobe maps, which is, in fact, the source of discrepancy here between these spectra. Now, we can look at the power spectra for the region with medium emission. So this was this green region in my mask. So this is not just masking the central part, it's masking the central part, but also the cleanest sky, so that we compute the power spectrum in this intermediate emission map. And so we can see here that we have a very good agreement, again, between the two. We have now a little bit of excess of Cosmoglobe as compared to my maps here, around L equals 100 or so. And we see here with the crosses, what we get after I debias my spectra here from the noise. So we see these nice power laws here. And this is in the cleanest part of sky. We see now that very clearly the Cosmoglobe maps have a spectrum which is above the spectra of these Planck revisited maps, which means that there is extra noise. So extra noise here, extra smoothing here. These are the power spectra after they are debiased from the noise. We see that the B modes are slightly below the E modes, but not by a huge factor. And the spectrum looks very much like a very straight power law. Well, within small. There are in fact some oscillations here. There is some correlation between points because of the mask, but presumably some of these oscillations are real. So it's not a real, I mean, it's not a perfect power law, but it's close to a power law. At least there is no curving of this trend here. Okay, so to summarize on synchrotron, new synchrotron polarization template. We have a new synchrotron polarization template that's significantly less noisy than DR3 released Planck maps. So noise characterization is better. The angular resolution is reasonably well defined, and these maps can be used for better synchrotron cleaning in upcoming ground-based CMB experiments. The data products are available from this portal here at NERSC. I want to I forgot to say that if we compare at the same angular resolution, so after I smooth the Planck revisited maps with an extra 30 arc-minute to put them at the same angular resolution as the Cosmoglobe DR1 maps, the Cosmoglobe noise level is about 3.4 microK arc-minute, and for Planck revisited, it's about 2.3. If you are interested more in the spectrum than in the standard deviation, it means 11.6 for Cosmoglobe and 5.4 for Planck revisited, which means a factor of a little bit more than 2 better. Okay, now, are there questions on this part before I move forward?
I have one question. So how you take into account calibration error between the WMAP and the Planck?
Sorry, can you repeat?
How you take into account the calibration error? So like WMAP and Planck has a slightly different calibration, like overall normal calibration error. So
yeah,
that is your spectral index you take into account.
So I don't recalibrate.
Okay.
I think there is a slight calibration error, but there is also an error which is due to the fact that, as we know, the synchrotron spectral index is slightly changing. So you see, this calibration error will generate an error which will be proportional to the signal. And so because I'm interested mostly in the regions where the synchrotron is faint, this error will be subdominant. So I don't make any particular effort to correct for that. We could, if there are specific reasons to do that, we could try and take that into account. But each time we try to correct things like that, measure things, additional parameters and so on, we lose in signal to noise. And in particular, it makes sense to correct for that if we also take into account the fact that the spectral index varies across the sky, and then there is immediately a noise penalty which is paid. It's a very standard problem of noise variance versus bias compromise. And here I decided to do the compromise that we minimize the noise as much as possible. And then, we can do post-analysis if we want, maybe just, compare again with the original maps, etc., to see where there are discrepancies.
Okay. And another question is this cross power spectrum that you showed between Cosmoglobe and your map in the intermediate region. So it has a less power, no? So it does not
go. Okay, so I don't do a cross spectrum between Cosmoglobe and my maps. What I do here is I compute the power spectrum for my map here in gray, and these are autospectra for E modes in black and B modes in gray, and there are autospectra for Cosmoglobe in red and in orange.
Okay, and the lower ones are the
and the lower ones with crosses is after I subtract the E noise or the B noise from my plane line spectra. So you take this line here, the black line, subtract the noise, and you get these black crosses here.
Okay. Okay.
And same thing here.
Okay. Thank you.
Okay, so the second part of the talk is about improved maps of galactic CO line emission. And this is work which was done with Mathieu Ramazai and Shamik Ghosh. In fact, we started that almost 10 years ago with Mathieu, and we never completely converged. And then we asked Shamik to take over, and so he finished the project. So this was published also this year. This is Shamik here. And in fact, most of the slides he prepared on the basis of what we have done for this project. So I want to give him credit for that. So the CO emission is well known. It's been detected in Planck. It's a carbon monoxide molecule. It's very abundant in the galactic interstellar medium. It emits radiation at 115.227 gigahertz through the rotational line J equals 1 to 0, and at multiples of that frequency for lines at J equals J to J minus 1. This shows here the CO ladder from J equals 1 to 0 at 115, and all the multiples of this sort of fundamental frequency. This is for the main CO line, 12C16O. We have isotopologues such as 13CO or C18O and C, in fact, 17O, etc. And they emit at slightly different frequencies, closer to about 110 gigahertz and multiples of that. The CO line is very interesting because it's one of the main cooling lines of the galactic interstellar medium, and it's also a tracer of the interstellar medium in cold and relatively dense phase, molecular clouds, and so on, neutral medium. CO lines are present in several of the Planck HFI channels and was notably detected in the 100 and 217 and 353 gigahertz channels. And maps of CO emissions were produced by the Planck collaboration as part of the first and second data releases. And the data products are available from the Planck Legacy Archive. There is one paper on Planck galactic CO observations. It's from the 2013 results. And then the products were improved with the second release, but there was no... I'm not sure there was another publication. I should check. Okay, anyway. So these are the lines in the Planck bands. So we see here the J10, the first line in the 100 gigahertz. Here in the 217 gigahertz, we have a CO line, and in the 353 gigahertz. There are also lines in these other channels, but the ratio of CO to dust becomes very small, because CO decreases while dust increases. And so in the end, they are very difficult to detect in these channels without doing spectroscopy and looking specifically for the line. We have three versions of Planck CO maps, which are called Type 1, Type 2, and Type 3. The Type 1 use the slight differences in Planck band passes within one frequency channel to separate CO from dust and CMB. So essentially, we have channels which look like that, but they are slightly different for various detectors. So if you take detectors which are all in the same frequency, we have a mixing matrix for CO, which is different from the mixing matrix for dust, or mixing column for dust and CMB. And it's possible to exploit that to extract the CO maps. So this is what is done for Type 1. There is then one map per frequency channel. So one at 100, one at 217, and one at 350, which correspond to these three lines. It gives the best separation of CO from dust and CMB, but is noisy. There is also some mixture of main CO and isotopologues, which yield some calibration uncertainty. Unfortunately, we have these CO line at 110, which is slightly moved here, and so which doesn't have the same response. And so there is some mixing between these two isotopologues. The correlation between the various lines is not exploited in this analysis because the analysis is done independently for each of the lines. And so as a consequence, these maps are very noisy. For type 2, a multi-frequency fit was made of CO plus CMB plus dust plus free across several frequency channels. And it was done only for two lines, 1 to 0 and 2 to 1. As a result, because it used already band average maps, it's much less noisy than type 1, but it's model dependent because it assumes some spectral emission for free and dust with fixed beta and T dust for dust and fixed also emission low for free. And also it neglects, for instance, that there is SZ also in these channels. And so for the first line, the channels which are used are 70, 100, 143, and 353. And you can sort of understand how this is happening in the end, because 143 will be measuring the CMB, 70 gigahertz will be measuring a combination of free and CMB, and so will give us the level of free. 100 gigahertz is where we measure the CO line, and 353 gives the dust, neglecting the CO, okay? And same thing for 2.1, again 70, but now 143 gives again the CMB, 217, where there is CO, and 353. And then there is type 3, which is based on an early version of Commander. For the paper I'm mentioning at NSide equals 256 only. A new Commander map was produced later on, published in 2016. But as I will show you, it still has, it's not significantly better than this one in terms of noise in particular. So we have here these maps. So we don't see much here. These are type 1, type 2, and type 3 for the first line, type 1 and type 2 for the second line, and type 1 only for the, sorry, line 1 only, sorry, line 1 only for type 3 maps. They all look similar here with this color scale and with this big full sky view, but these are the noise maps, and there is one thing which is striking. This is noise for the type 1 map. It ranges here up to 60 in whatever unit. This is KKMS, while for type 2, it's 1.3. So it's a factor of 40 or so, 40 to 50. So this map is much, much less noisy than this one. And this one, which is a type 3, as you can see, it's more noisy than this one. And so it doesn't bring so much. We also have only one map, only for the first line. It assumes a constant line ratio between the various lines. Okay, same thing here for the 2.1. We see here that the noise level in the type 1 is much larger than in type 2. And so what this calls for is to try to recombine all of these data to get the good signal-to-noise ratio of the type 2 maps, but the clean maps with low contamination of the type 1, low contamination of other foregrounds. I can show some detail. So there is one more thing which I should mention is that these different data products are not completely consistent. This is the power spectrum of the type of the CO10 line for type 1 and type 2. And you can see that they are different. There is a significant factor between the two. And this is for full sky. If you go to do a minimal mask here, which is shown here, they are much more compatible, but still there is some discrepancy. So this is here very easily to identify as being leakage of some dust or free or both in the type 2 CO map. And this is for the 2-1 again. So we have type 1 and type 2, and we see that they are a little bit discrepant. It's better here when we mask the main galactic region. If we make an histogram of one map versus the other, we see that they don't follow a line of 1 for 1 here. So there is more 1, 1, 0 CO in the type 2 map than in type 1, but there is less type 2 CO in the type for the 2 to 1 line than in type 1. And this here shows that in the clean region of sky, this is not seen because everything is below the noise. We have also artifacts. So this is the third CO line across the galactic plane. We have this bouncing here, which is due to some kind of filtering. And now if we look, for instance, in this region here, polarized, this is here the type 1 map, where we now see very clearly the noise. So we see here 1, 0, 2, 1, 3, 2. We have this structure here, which is visible in 1, 0, still visible in 2, 1, and difficult to perceive here in 3, 2. And here it's been smoothed to 20 arc-minute to try to see something. This is here smoothed to 10 arc-minute, and this is smoothed to 20 arc-minute. There is compact source contamination in type 2 maps. We have here type 2 maps in different regions. And here we have, for instance, the Crab Nebula, very visible. We have here some radio sources and some sources which are positive and some which are negative. This is a Tarantula Nebula in the LMC, which is very visible. We also have these strange artifacts with this kind of moire effect in the pixelization, which is not nice. So these maps are not perfect. We have also clusters. This is here the North Galactic Pole. We have the Coma cluster, which is negative. This is the Planck type 2 CO map. So it's negative for the CO10 line and positive for the CO21 line. This shows that it's not CO in the Coma cluster, right? Because CO cannot emit negatively. And here are other clusters in different regions of the sky, which are clearly visible in these maps. So we want to correct that. So I won't go into all of the details of the processing, but essentially this thing, we do an extended GNILC, and I'm getting late with time, so I will go very quickly through that. Essentially, we are doing a GNILC, which is this generalized needlet ILC, but with a small extension, which is that when we don't directly detect something with high signal to noise in the data, we use a prior on the line ratio between the various CO lines. So just to remind you, the general principle of GNILC is to do a PCA, principal component analysis. We look and we keep only the dimensions which are significant and throw away the rest. And this does denoising. But here what we do is so that we, in regions where we don't detect clearly the CO, where otherwise the maps would be much smoother, we put a prior on the line ratio, and we produce a map anyway using a generalized least square averaging of the various maps. Okay, I have to skip the details, unfortunately, but this is what we get. So this is the output map we have for the first line as compared to the original type 1 map for Planck for the first line. And this is here the noise maps, corresponding noise maps from jackknife maps. As you can see, the noise level has been reduced very drastically. There are here some inhomogeneities in the noise because of the needlet processing. So we keep more signal here, which also injects more noise as a function of scale and location. But this map is much, much cleaner than this map. We see also that the map we produce with XGNILC is very well correlated with the input map as compared to what I've shown you before between type 2 and type 1 here, which are discrepant. So although we are using the type 2 to give us a better signal-to-noise ratio, the procedure adjusts the level locally in needlet space so that it's compatible with the CO10 observations in type 1. We have good agreement between XGNILC and type 1 at low L, with some discrepancy at high L, which is probably due to some mismodeling of the noise using the jackknife maps. There is probably some correlated noise, maybe due to point sources or things like that in the type 1 map, as compared to what we had before, okay? I just want to show a few images, now comparing and validating this data product against a spectroscopic measurement done from the ground by Dame et al. So here we focus on some regions which have been already shown in the Planck paper. So first of all, this survey is not full sky. You can see there are regions of sky which are missing. Now, with our product, we get also the data in these regions. And we can see here, for instance, a small patch of CO emission, which was not observed here. We see also that these maps are very compatible between what we get and what is obtained, and is not used in the analysis here we do at all, right? We just use it to compare. And so we are quite satisfied with the consistency with this external data set. And here, just to compare how much cleaner the maps are compared to the noisy type 1 maps, which are shown here, okay? This is the difference between the type 1 and the XGNILCs, showing that we see only noise. We don't see anything which seems correlated with the signal, again, for these three fields. This is now to show that we detect in these new maps high latitude clouds. So this is at high galactic latitudes, regions where it's very difficult to see anything in the type 1 maps. So here we see something. These regions for the XGNILC data product. And this is now results which for focused observation on some of these molecular clouds by Dame and Thaddeus in 22. And again, we are satisfied to see that there is very good consistency, but that we also detect things which are not present in these maps, which are not full sky. So this was all for CO10. I can show also CO21, where we see the improvement here on these fields between what we get here in the middle and the original Planck maps, and also for 3.2, where we didn't see much here, but here we have reasonably clean maps of these clouds. Okay, so just to summarize on CO, with a dedicated post-processing pipeline, we have these new low noise maps of CO. They come with some noise characterization, which is obtained. Sorry, so this is wrong. It's not by propagating of simulated noise. This is just from propagating jackknife maps through the entire pipeline. I have to correct that. And again, the data products are available from here. And that's all. Thank you for your attention, and I'm ready to take questions.
Thank you. Time for questions. If you have any question, raise it. Yeah, Sarvesh.
Are these CO lines, are they contribute to the polarized microwave sky?
Oh, so this is something which is still not completely clear. So there is some polarized CO emission. It's faint. The maps we have produced are just intensity maps. I think assessing exactly what is the level of polarized CO emission is still to be done.
And most of it is around the galactic plane, the emission from CO.
Well, so it's mostly for close to the galactic plane, but not only, right? If you look at these maps, let me show maps again. So do I have a full sky map? Yeah. So you see, this is there is here CO. Obviously, in the galactic plane, you have clouds like here, here. You can see it even on the. I don't know on your screen how well it is, but on mine here, I see here very, very easily these things. And, you know, some of these clouds here so you see this one here, for instance, is at -69 galactic latitude. So it's high galactic latitude.
So apart from synchrotron and thermal dust polarized component, we expect more type of components in our microscope.
Yes, 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 of course. So we are working also on Planck data to get better maps of other components, starting with dust. So Elisa, my current graduate student, is working on that. She has made good progress, but it's not ready to be shown yet. And but here, I mean, specifically, we have concentrated for the moment on these two data products. There is a lot more to be done, and in fact, collaborators are welcome.
Okay. Thanks.
Yeah. Any other question?
Yeah. Hi.
Right.
So you were showing from the first part when you were showing the synchrotron maps and also the scanning strategy of WMAP and Planck. I just wanted to know why WMAP used that scanning strategy and why we moved to a different scanning strategy for Planck. And
yeah, so it was a choice, and the two experiments had different constraints. So they had different constraints on scanning speed, and they had different. They made different choice in terms of you know, how to change the solar aspect angle. The Planck instrument has bolometers on board, and bolometers, they are very, very sensitive. And so there was a concern that if we change the solar aspect angle a lot, in particular, if the sun, you know, you don't want the sun to shine on the screen. And so the solar aspect angle for WMAP was larger than for Planck. And so there were a number of constraints which resulted in these two very different scan strategies. And because of that, it turned out that they are more sensitive in different regions of the sky. Did I answer your question?
yes, thanks.
Okay.
I have one question. So in this slide, this DAM 2022 map, so you see some extra emission in your X-GeneLeaf map in the first column, but not in the DAM map. So that is because it's not covered, or it is?
Yeah, it's not covered. It's not in the set of. So these maps have been obtained from the data using the flags which show where the data is considered usable in this particular survey. And so this particular cloud was just not observed with enough observation time or whatever, and was not included in the available data.
Mm-hmm. Okay. Okay. Any more questions? If not, so let's thank Jacques for giving this broad overview of all the new Planck full-round maps and the results. So it's very encouraging.
Thank you for inviting me to give this talk. It's a pleasure to see you, even if it's on video. And you know, I wish I could I could give a talk in person, but it will be for another time, I suppose. Okay.
Thank you.
Is something in the chat? No?
Oh, no.
No. Okay. Bye, everybody.
Thanks. Bye.
Thanks, Jacques.